Okay, miscellaneous announcements. First, I got an email from Dean Higgins that I should remind people about these online course evaluations. This is the first time the Extension School has done these online, and when the college switched over a couple of years ago, I discovered that in courses where I'd been getting 100% returns on these by passing them out in class, I was now getting 50 or 60%. So please send them in. This information is very useful to me, and it's very useful to the Extension School. So please remember, before next week's class, get online at this URL and fill this out. Why they cut it off as early as next Monday, I don't know, but apparently that's the date.
Only till next Monday that they're available?
Only till January 9th, they said. It must be that...
Is that true in the college also, or just at the...
Yes, I think so. I think that in the college, the last day of reading period is the last day for filling these out. And I think that if this course met at 5:30, there would be an exam on Tuesday of next week. So
Yes,
I think that's the last day before the first exams that can be given. My thought is that for next week, I've got this room, and assuming there's interest, I'll check in a minute. What I will do is, over the weekend, perhaps late Friday, I will email out last year's final exam with the strong suggestion that what you do is sit down and get someone to check that you're spending no more than 2.5 hours on it. And then I will attempt to work the exam in 2 hours next week and answer any questions about it. Now, I should warn you that I actually created 2 exams by writing enough questions so that I could make 2 exams out of it. I then split the pool of questions up into 2 exams, and last year I asked my grandson, who was 3 at the time, to pick one. So he picked one, and that was the final. I'm sitting on the other one, but that means you'll have to do some careful estimates of conditional probability in deciding whether, for example, if there's a Monty Hall question on the practice exam, there is likely or unlikely to be a Monty Hall question on the real final exam. The 2 exams were drawn from the same pool and have a lot in common, but they're not clones of one another in the same way that the make-up quizzes were clones of the original. So can I see a show of hands? Do people feel this is a useful way to handle next week? Okay, so we will do that. And of course, you're welcome to come with the exam not filled out, but I think it would be good practice to sit down and do it, and then if you do really well, you can stay away. If not, my explanations might provide you with some useful clues. The material, yeah, Robert?
Do you know if Chris is going to be around? He had talked about doing a review as well.
Yes, Catherine and I were talking about this afternoon. I thought that given that I was doing the old exam early next week, that Chris's alternative proposal of having something closer to the date of the actual final now made more sense. Does that seem reasonable to people?
Yep.
And he'd proposed a specific date, had he not? Or
he had like 3 dates.
Okay, so I will pass the word to him, and you folks can independently via the bulletin board that some date closer to the final will be useful. That will give you 2 independent reviews done by the 2 of us. Other administrative issues?
I just wanted to clarify the practice exam, or the exam from last year,
Yep.
is in addition to and separate from the practice exam that you will mail out?
No. That is the practice exam I will mail out. What I will do is I will mail it out over the weekend, giving you time to work it, and then I will solve it in class.
Okay, so that's it for practice exams.
That's it for practice exams. But this will be a real practice exam. And I would ask you and the folks who are watching on the video, If I were doing this entirely on paper, I wouldn't worry about reusing the questions at some point in the future. I'm a little concerned where I'm going to have to email this out. So I'm going to ask everyone, please, if you will, print a copy and then destroy the electronic version. I'm just afraid that an electronic version could get posted somewhere, and then I've got all these wonderful questions that I can never use again. So treat it as a read this message and burn it sort of email attachment.
So you're not going to tape next week's session?
Yes, I am going to tape
You
next
are,
week's session.
and it will be videotaped?
Yeah.
It'll be on the website?
Yeah.
Okay.
Yeah. No, it's clear once I tape this, if I make it available to other people in this course in future years, it will have to remain a practice exam, and that's probably what it will be. But I teach this subject in other courses, and I don't want my undergraduates snooping around extension school websites to see if they can find some of my old questions. Okay, so the material I'm going to talk about tonight is not going to be on the final. I reserve the right to ask a trivia multiple choice item on it, but nothing probing, for the simple reason that there's not time to do any homework problems on it. Nonetheless, this is material that is a standard part of first courses in probability, and I will introduce toward the end a subtle but very useful and interesting distinction between the weak law of large numbers and the strong law of large numbers, which you'll probably be able to ponder for 5 or 6 hours before you really understand it. So here goes. The first thing, I'm taking the title from the book. This is number 1, called The Basic Inequality. And as you'll see when I prove this, it's kind of trivial, except that there are special cases of it that have people's names attached. So this is one of these simple results in mathematics that's so important that various special cases of it bear the name of the person who first wrote down that particular corollary. So here's what we've got. We've got a function of a random variable. The function is little f, and this function has the property that it can never achieve negative values. It's either 0 or positive for all values of x, positive or negative, and that means that the absolute value function is okay, but not the identity function, because for negative x, the value of the function x is negative. X squared or x to the 4th will be okay, and in fact those will be the two other cases that we use. But x cubed would not be okay. And I'm going to do a proof that's essentially the same proof but that it's in the book, but I think I have a more straightforward way of stating it in terms of conditional expectation. What I want to do is to calculate the expectation of this particular function of the random variable. For example, to compute the expectation of the square of a random variable, which is crucial to calculating the variance, as you know. And I want a condition on the event that the function f applied to the random variable x gives a value greater than a. Well, you should know how to do this now. I'm going to calculate the expectation of f of x, and I want to write it as the sum of two terms. One term that applies in the case where this event occurs, and the other term for the case where it doesn't. So what should go in my first term? the probability that f of x is greater than a multiplied by
The conditional expectation.
the conditional expectation of f of x conditioned on what?
That it's greater than
That it's greater than a. And then I have to add on to that the probability of the complementary event, namely that f of x is less than or equal to a multiplied by the expectation of f of x in that case, where f of x happens to be no greater than a. Now, the reason I've done this is I'm now going to make a couple of very crude estimates. And when I do corollaries of this theorem, which you'll be doing for the rest of this evening, there will be many cases where you say, yeah, that's true, but it's a really lousy estimate. I don't care. These estimates are what we need in the case where we're adding together a very large number of random variables. And while they're not very tight estimates, they're extremely general. So now what I'm going to do is say this was equal to the line above, but if I'm willing to write greater than equal than, I can replace these conditional expectations by something that's simpler and smaller. So again, I've got the probability that f of x is greater than a times something that's no bigger than the conditional expectation of f of x, given that f of x is greater than a. So let's think of a concrete example, and you'll see it. You have a lottery ticket, and you know perhaps that the lottery commission returns 60 cents on the dollar. You paid $10 for this ticket. You might say the expected value is worth $6. And then someone says to you, I snooped at the serial number on your ticket and hacked a few websites, and I can tell you that that lottery ticket is guaranteed to win a prize that's at least $100. So now you ask, what's the conditional expectation of the value of that lottery ticket, given that that value is at least $100? And what's a nice conservative lower limit for that expectation? $100. Worst case, it's a $100 ticket. So what I'm going to do is just write A here. I mean, in the case of the lottery ticket, and in many cases, you'd hope this conditional expectation is much greater than that, but it's at least A. Okay, wait till you see what I do with the other one. Even the Massachusetts Lottery Commission has not found a way that after you scratch the ticket, you end up having to pay the state money. So the value of a lottery ticket has this property of being non-negative, which is one of the few good things that one can say about it. And therefore, give me something that is certainly no greater than the value of your lottery ticket if it can't be worth even $100. Zero. Okay?
Paul, can I be fussy? What about the cost of the lottery ticket in the first place?
You already paid that. What I'm talking about is the expected value of it after you already have it. Yeah. The expectation on the whole transaction is definitely negative. But once you have the ticket and you've paid your money, the expectation is positive. So I actually use this property. Okay, so this term goes away, and now what is usually done with this is to write it backwards, to say that the probability that some function of a random variable, x, is greater than a is less than or equal to the expectation of f of x divided by a. When I first saw this, I thought that it looked extremely profound and mystifying, but it's a completely trivial statement. What it's saying is that if the probability of this event were any larger, then the expectation would have to be greater than the stated value. And you'll see this again and again in special cases. So everything else is going to be derived from this silly little formula. The first consequence I'm going to derive is known as Markov's inequality. Markov is a famous name in probability theory. You'll discover a lot of the famous names in probability theory are Russian names. It was really the Russians that codified this subject in the 20th century. So this first simple corollary is known as Markov's inequality. And I'll give you the stupid example first and then show you how you can refute this. Anyone ever taken a pre-med chemistry course? Yeah, I once took organic chemistry. And I'm always hearing advisees complain about this. Things like, oh, in my chem what's-it course, we just had a midterm exam, and that was so hard. You know, it was so hard that the mean score in the class was only 30 out of 100, but some of those pre-med study so hard, and I've just been told that 40% of the class got over 93% on that exam. So that's doubly worse than my 70. I'm never going to be able to practice medicine. So think about that. Average 30%, 40% of the class got 93%. Even in freshman chemistry, that can't happen. And Markov's inequality is what we need to shoot down such statements. For Markov's inequality, we use as our function f the absolute value function, or equally good, the random variable x cannot assume negative values. If it's possible to get minus 250 on this chemistry exam, then the statement that I just gave you could be true, but we're assuming that scores on chemistry exams are non-negative. So, what do? I take my general result. For f of x, I write absolute value of x, and I say that the probability of that the absolute value of x is greater than a has to be less than or equal to the expectation of the absolute value of x divided by a. That's Markov's inequality. And for my chemistry example, one claim that was made is the probability that the absolute value of the score, which is equal to the score since the score can't be negative, is greater than 94 was equal to 0.4. The other claim that was made was that this was a very hard exam, so hard that the expected score when a student took a test was equal to just 30. And you notice that I was sort of wavering in saying average versus expectation. Life is very clean when you're only talking about probabilities. If I say, I have written this chemistry test, the expected score on it when a randomly chosen student takes it is 30%. I can talk about the probability that a randomly chosen student will get better than 70% and so on. The minute I start talking about the actual average score that was achieved when 57 students took the test, or the percentage of students that get better than 94%, now I'm not talking strict probability. I'm really venturing into the domain of statistics. Those of you who have done the first computer project got good practice with this because you were supposed to plot both the mass function for one of these probability distributions and then the actual numbers that you got by running a random number generator a few hundred or a few thousand times. and they don't agree. They get better and better and better as you do more and more experiments, but they never agree completely. I'll explain the details of that in about an hour's time. So here are my purported results. So A is 94, and let's check this. Markov says the probability that the score on the exam is greater than 94 cannot exceed the expectation on the exam, which is 30 divided by 94, and that's what, about 0.32. So the claim that 40% of the people got above 94 has to be wrong, and the simple reason for this is that if 40% of the people who took the exam got 94 and the others all got zeros, that would still bring the average up above 30. That is, there is very, very little to this, but it will enable us to prove some incredibly far-reaching and useful results. Another example. You buy a $5 scratch ticket. You know that the expected value of that ticket once you bought it is $3. What can you say about the probability that you can cash that ticket in for $100 or more? Less than or equal to what? Come on. 3 over 100. For the simple reason that if this ticket had more than a 3% chance of being worth $100, then the state would end up paying out more than $3 per ticket, even if the ticket was worthless under all other circumstances. Okay, that's Markov's inequality. The next one is called Chebyshov's inequality. This is the most famous of these. And the spelling is unusual, but I agree with Sturzacher that this is the correct transliteration of the name because the name in Russian is pronounced Chebyshov because after the sha consonant you can't have an a. So you'll see this guy called Chebyshov. He's got a bunch of polynomials that he's famous for also. But his name should be pronounced Chebyshov, and we'll spell it that way. He achieved this little bit of fame by choosing the squaring function for his little f, and also by considering the special case where the expectation of x is equal to 0. This is not a significant restriction because if you have a random variable where the expectation is 1, all you do is subtract off 1 from the random variable and you have 1 where the expectation is 0. The nice thing about assuming the expectation is 0 is that then the expectation of x squared is the same thing as the variance. Okay? Just use the same basic formula. But now what I'm really interested in is the probability that the absolute value of x is greater than a. And that's the same thing as the probability that x squared is greater than what? A squared. And we know what that is. That's the expectation of x squared divided by a squared. Because the rule is always whenever you want something that's bigger than a probability like this, you take the expectation of the function of the random variable, put it in the numerator, the thing you're comparing with, and you put it in the denominator. Now, because I'm assuming that the expectation of x is less than 0, I can also write this as the probability that the absolute value of x is greater than a is less than or equal to the variance of x divided by a squared. So this is nice. Anytime we have a random variable with an expectation of 0 and a well-defined variance, and we have from time to time seen weird random variables where the variance was undefined. But if the random variable has a well-defined variance, then the probability for large values of x has to fall off at least as fast as 1 over a squared. This again sounds very profound, but it isn't. This is true for the simple reason that if the probability didn't fall off that fast, when you went to calculate the variance, you would get a sum that diverged, and you wouldn't have a variance to start with. So the only way you could have any hope of calculating a finite quantity when you compute the variance is that the probability falls off at least that fast. Let's look at an example. You make 10 bets on a fair roulette wheel, and associated with each of these bets is a random variable. For the first bet, for example, your payoff is a random variable, which I'll call x1, which is +1 with a probability of a half, and -1 with a probability of a half. Now, what we're actually doing is adding 10 of these together. And the question is, what is the probability that your total winnings for these 10 bets exceeds $8, where by S10, this is notation consistent with what I'm going to be using more generally, I mean x1 plus x2 plus ... plus x plus S10. Pardon?
Greater than how many dollars? I can't.
Oh, greater than 8.
Okay.
Now, this is actually a perfectly easy question to solve. That is, you can easily calculate the probability that if you make 10 bets on a roulette wheel, say 10 bets on red, that you will get 9 or 10 reds or 9 or 10 blacks. And if you do that, you will come up with a much smaller value for the probability than the estimate that I'm going to give you. Nonetheless, the estimate that I'm going to give you is correct. It's just not a particularly good one, not a particularly tight one. The probability that the absolute value of S10 exceeds 8, I'll drop the $sign, is less than or equal to what? Well, we've got to calculate some variances here. What's the variance of this random variable? It's got an expectation of 0. X is either +1 or -1. So x squared is guaranteed to equal 1. What's the expectation of x squared? It's 1. Okay? You add 10 of these together. Now remember, I proved last week that if you sum independent random variables, the variance of the sum is equal to the sum of the variances. So what is the variance of the amount that you win by playing roulette 10 times rather than just once? You play roulette 10 times. There are 10 random variables. X1, your first play. X2, your second play. X3, your third play. We agree that each of these x's has a variance of 1. And furthermore, these are independent random variables. The probability that red will come up on the fourth spin and on the sixth spin is equal to the probability that it comes up on the fourth spin multiplied by the probability that it comes up on the sixth spin. So if the variance is 1 for one play, what is it for 10 plays?
10.
10, yes. Notice, it's crucial that these random variables be independent. If the croupier says, I'm feeling lazy, I know you're planning to make 10 $1 bets, but I want to go home. Why don't you just plunk down $10 and we'll pretend that it was 10 $1 bets. In that case, you either win $10 or you lose $10, and the variance is 100, not 10. But if these are independent, the variance is 10. So here we go. This is less than or equal to the expectation, to the variance of x, variance of Sn divided by 8 squared. And the variance of Sn is 10. So the probability that you will win or lose $9 or $10 is less than 10/64. It's actually a whole lot less than 10/64, but that's consistent with being less than 10/64. Okay, now, question? No, I'm going to generalize this and get the weak law of large numbers. The 26-character version was large numbers weak. So this is just an abstraction of the roulette example I gave you. We'll have a random variable S sub n, which is x1 plus x2 plus ... plus xn. And these random variables are independent. They're identically distributed. And each of them has an expectation of 0, and each of them also has the same variance. A familiar example of this sort of situation is a random walk. This is exactly what we do in a random walk, because one example of a random walk is what happens to you when you play roulette. For each play, you either go up a level or down a level. x1, x2, x3, and so on are all either +1 or -1. And your total winnings after you play n spins of the roulette wheel is S sub n. So this is a situation we've been talking about, except now we're not concerned so much with the details of the random walk as to where you get after n steps. Each of these has the same variance, so I will refer to this as the variance of x. Remind me what the variance of S sub n is? It's the sum Yes, but if they all have the same variance and there are 10 of them, it's n times that. Thanks. So as Jerry's just said, the variance of the sum of these is n times the variance of any one of them. And now what we want to do is to calculate the probability that S sub n is greater than A. And we can do that by Chebyshov's inequality. That's the expectation of x squared, which is n times the variance of one of these things, divided by a squared. Now what I'm going to do is I'm going to write A as n times epsilon, or epsilon is equal to A over n. And that's like asking in conjunction with roulette, what's the probability that I will win or lose an average of, say, more than 3 cents if I just make a long sequence of $1 bets? To say an average of more than 3 cents would be to say I make 10 bets and the net effect of those, better do 100 so the numbers work out, that I make 100 bets and either win more than $3 or lose more than $3, or that I make 1,000 bets and either win more than $30 or lose more than $30, or that since I've got 5 weeks of hotel accommodations in Las Vegas, I make $1 million $1 bets in succession and either win more than $30,000 or lose more than $30,000. And I think we all have a sense that the probability of winning or losing $10, $3 or more on 100 bets is not that small, but winning or losing 10 times that much on 10 times as many bets is significantly less likely. And you'd really expect, if you played a fair roulette wheel a million times, that your expected wins, your expected net win or loss for that amount would be a tiny fraction of a million, right? So this is what the weak law of large numbers is going to tell us formally, because I'm just going to substitute in here epsilon equals A over n, and I get that the probability that S sub n is greater than A is less than or equal to n times the variance of one of these divided by n squared epsilon squared. I can cancel 1 power of n, and I discover that the probability that my total winnings will exceed A, or equivalently, the probability that my average winnings will exceed epsilon, because if I divide S sub n by n, remembering the absolute value signs, and divide A by n, when I divide A by n, I get epsilon. So what I find is that the probability that my average win or loss per play will exceed some small number epsilon is less than or equal to some constant, which depends on my choice of epsilon, divided by n. And the divided by n is the crucial thing. That tells me that if I play the roulette wheel 10 times longer, thereby increasing n by a factor of 10, the probability that I will win or lose a certain percentage of the total amount that I bet goes down by a factor of 10. And this is what you need to know if you're going to run a casino. Because you open up this casino, you've got a certain amount of capital behind you, and you say to the mathematician on your staff, hey, I'm a little worried about this. Suppose the folks come in and they keep winning and winning and winning, and he says, look, boss, don't worry about it. You've got the law of large numbers on your side. If people play the roulette wheel 100 million times, which I suppose is not unreasonable, the probability, even if you don't use zeros on the wheel, that the total amount that they've won or lost on the average per play will exceed 1 cent is going to be some number divided by 10 million. And if that's not good enough, you go to 100 million or a billion. But if there are enough people playing in this casino, the probability that the total amount they win or lose will come out very, very, very close to the expectation that we've calculated for that roulette wheel becomes very high. This is what most people know as the law of averages, that if you do an experiment enough times and average things together, that the average that you get gets closer and closer and closer to the random variable that represents that experiment. Everyone comfortable with this? Yeah, Robert?
I missed something where you brought in the c. That's the variance of x over epsilon squared.
That's right.
Does c have any? Why?
Oh,
Why
because
bother something out?
I want to stress that the only thing I'm interested in is the fact that it goes like 1 over n. Everything else is independent of n. So it is, in fact, the variance of x over epsilon squared. And if you pick a small epsilon, 1 over epsilon squared is a mighty large number. But nonetheless, when n gets large enough, it doesn't make any difference how big this c is. I can always pick a little n that's so large that this probability becomes as small as I like. That's the key result. Let me give you a couple more examples. Sneak this in a different color. That color readable?
For now.
For now. Okay. Tell me when I have to go back to green. And this is a simplified version of an example associated with the great mathematician Borel. This is a very special case of something called Borel's normal number theorem. You may know that there are people in the world who compute enormous numbers of digits of pi. I think the current record is 2.2 trillion digits. And you might have wondered why people do this. Well, there are a number of reasons to do it. One is that it's fun. Another is that it gives you bragging rights. And another is it's a great way to check computer hardware. That is, if you have 2 brand new computers that you've just built, and you use both of them to calculate 10 million digits of pi, and they agree in all 10 million digits, the probability is overwhelming that you got that agreement because they're both correct and not because they happen to have exactly the same hardware and software bugs. But the real mathematical reason that people compute lots of digits of pi is there is interest in trying to figure out whether or not pi is what is called a normal number. So now I have to explain to you what a normal number is. This is a concept that is due to Borel. So what we're going to do is generate a random real number. This is a continuous random variable, strictly speaking, not part of this course, but I think you can accept the concept of generating a real number which is equally likely to have any value between 0 and 10. Basically, the idea is you slash the number line at some point, and that's it. And you might get something that looks like this, 3.14159, and so on. But if it's a random real number, you would expect that each digit is equally likely to have any of the values 0 through 9 inclusive. That is, if you generate a random real number by measuring the exact time at which a certain alpha particle decays, and then calculate the 8th decimal digit of the expansion of that time in seconds, you would expect that that digit is equally likely to have any of the values 0 through 9, right? I'm going to make this a little bit simpler so it connects with the previous example by saying I'm going to introduce a random variable xi, which is +1 if the ith digit is even and -1 if the digit I is odd. So for this particular number, counting just things after the decimal point, so this is going to be 1, 2, and so on, x sub 1 would equal -1. X sub 2 equals +1. X sub 3 equals -1, etc. And if we believe that each of these digits is equally likely to have the value 0 through 9 inclusive, what would you expect to get when you add lots and lots of these x's together?
0.
0, right? And what Borel's normal number theorem says...
Actually, Paul, there is one more odd number than even number in that set.
No, 0 through 9. I'm counting 0 as even, yeah. And I refuse to fuss about the issue of things that end in 0.99999 rather than 0.00000. So a normal number would have the property that if you add up the x's for lots of digits, counting 1 if it's even, -1 if it's odd, that's just a little device to make the expectation come out to 0. Then the expectation of Sn is 0. You'd be very surprised if you took someone's random number generator and discovered that you got twice as many odd digits as even digits. You wouldn't be too surprised if the first 5 digits came out odd, but if you calculated the first 3 million digits and 2 million of them were odd and 1 million were even, you'd say, there's something wrong with your random number generator. You better go back and recode it. So now what we can ask is, what is the probability that the odd digits exceed the even digits by, let us say, more than 1%? Never get a full board out of that blue one. Go back to green. So the probability of a 1% excess of evens or odds in n digits. This is something that we can calculate by using the weak law of large numbers. This is less than or equal to the variance of x for one of these digits divided by n epsilon squared. This is 1 divided by n times 10 to the minus fourth, or 10 to the fourth over n. Now, as I said, these estimates are lousy. If you plug in a value of n that is equal to 5,000, which most people think of as a fairly large number, it says this probability is less than 2. We knew that all along. But if you're thinking about n equals 1 or 2 trillion, you can see that if you believe this hypothesis that randomly generated numbers are normal, the probability of a 1% excess of odds over evens in 2 million digits becomes very, very small, according to this estimate. And what the people do when they calculate enormous numbers of digits of pi is they come out with a table. They say, we've got so many zeros, so many ones, so many twos, so many threes, and this is consistent with the hypothesis that pi is a normal number. You don't get exactly the same quantity of ones as twos, but you get them close enough together that anything you can calculate is within the limit set by the weak law of large numbers. And in the case of pi, this is kind of interesting because pi is one of the very few transcendental numbers, numbers that doesn't solve any polynomial equation with integer coefficients, that we can actually get a handle on. And it wouldn't be out of the question that pi was an exceptional number and didn't look like something that might have come out of a random number generator. But so far, the statistics are consistent with the hypothesis that pi is a normal number. And the only way to find out more about whether pi is a normal number is to compute the next 2 trillion digits. What you can't do by computing lots of digits with pi is to show that pi is irrational. If pi were equal to 3 trillion and change over 10 trillion and change, then what might happen when you actually did out the division longhand would be that after 10 trillion digits or so, the digits would start to repeat. You'd say, these guys have only computed 2 trillion. Same way, I write down 0.428. Ooh, that looks like the star of an irrational number. Now it looks like 3/7, doesn't it? But you've got to calculate 7 digits before you even get a hint that this is the decimal expansion of something with a 7 in the denominator. Okay, now before we take our break, I want to... No, we don't need all the time, and I'm going to play it safe. So let's call a halt to the first half, and when we resume, I will explain to you why this is weak, and then prove a strong law of large numbers, and show you why, for practical purposes, it's much nicer to know that something satisfies the strong law than the weak law.
Yeah, it's...
They really loaded it up.
What I want to address is the issue of why the epithet weak is applied to this law. And to do this, I'd like to put it in terms of a real-worldly economic example. We all try to budget, and we all know that no matter how skillfully we budget, we never hit things right on the mark. The most we can hope to do is to have the expectation correct in the budget. But we also might think that if we're good at budgeting and we budget over a very long time, we'll probably come out much closer to hitting our budgetary target than if we try to budget just for 3 or 6 months at a time. And so let's make this as our model. X1 might be the budget surplus or shortfall in year 1. X sub I will be a generalization of that, the budget surplus or shortfall in year I. And then S sub n, which is x1 plus x2 plus on up through xn, is equal to the net surplus for a full n-year period. And we would all expect the percent that if someone's good at budgeting, now there are people who systematically underestimate by 5%. This wouldn't be true for them. But if someone is good at budgeting, you would expect the percentage discrepancy between the actual amount taken in or spent and the budgeted amount to be much smaller over a period of 10 years than over a period of just 1 year. And that's what the weak law of large numbers says. The weak law of large numbers says that the probability that the budget surplus or shortfall averaged over n years, that is, I add them all up and divide it by n, is greater than some epsilon specified by the manager of the department. This is going to be less than or equal to some constant over n. In other words, the longer you let the budget manager stay in office, the smaller the probability that this fellow will turn out to have given you an estimate that's more than 2% off one way or the other. And that sounds pretty good. If someone's good at budgeting, it won't work out perfectly for every short period, but in the long term, the percentage discrepancy is pretty sure to be small. And in fact, one can make a rather strong sounding statement, namely that if you want the probability that the average budget surplus or shortfall is less than 0.1% to be very close to 1, all you have to do is wait long enough, and that will be so. The probability that after a very long time you will be off by a significant percentage is essentially 0. So why isn't this good enough? What's weak about this? Well, it turns out we can ask for and get a lot more. What I'm going to assume now is that this really is the model for the budget. If you model your budget as the sum of lots of random variables, how much you're going to spend on postage, how much you're going to spend on telephones, and so on, then you can actually get a much tighter bound on this than the weak law gives us. But I have invented a scheme where the weak law is exactly right. So here is a model that just satisfies the weak law. And here's how it works. In year n, the treasurer slips 1 up through n in a hat and draws 1.
In year n?
In year n, thank you. And if she draws a 1, she either spends a lot of money or fails to pay some bills to put the budget out of balance. By more than 1%. Now, we can certainly say, under those circumstances, that and I want to be, she does this in such an extreme way that it puts the average for the entire 10-year period, for the entire n-year period out of balance. After 1,000 years, this is going to be pretty tough. After 1,000 years, she puts the numbers between 1 and 1,000 into a hat, and if she draws a 1, she either has to bring in a lot of revenue or throw away a lot of money, so the average for the full first 1,000 years is off by more than 1%. But in that case, it is nonetheless true that the probability that the average amount by which the budget is out of balance is greater than 1% is equal to 1 over n, because I've invented a probability model that makes it that way. Okay. Now I want to introduce a new random variable. I'll call it y sub n. It's a really simple random variable. It's equal to 1 if the budget is unbalanced for the first n years, and 0 if it's balanced. So if after 800 years the actuals differ from the budgeted by less than 1%, y sub 800 will be 0. But if after 801 years the actuals exceed the budgeted amount by 1%, then y sub 801 will equal 1. And now I can invent a new random variable, y, which is the sum of all the y sub n's from n equals 1 to infinity. This treasurer is staying in office for a really long time, folks. So now we can ask an interesting question. We can ask, what's the expectation of y? As time passes, the probability that the budget will be out of balance at the end of any given year gets smaller and smaller and smaller. Nonetheless, we can ask, if we add up 1 for every year when it's out of balance and we keep going forever, what do we get? And this is a perfectly easy thing to calculate. This is equal to the sum from 1 to infinity of 1 over n. Right? You've got a 50% chance, you got a 100% chance it's out of balance after 1 year, 50% chance after 2 years, 33% chance after 4 years, 1 in a million chance after a million years. And if you add up all those probabilities, you get, what's the sum of this series?
Diverges.
It diverges. And since I realize that I officially assumed nothing coming from calculus courses, let me show you a really quick proof of this. So let's write down this series. Okay, that's 1. That's a half. Someone tell me something simple that's greater than 1/3 plus 1/4. How about a half?
Less than
Less than a half.
No.
You said greater than 1.
Oh, I misspoke myself. Yeah. So 1/3 plus 1/4 is greater than a half. If you add up 4 things that are all 1/8 or greater, that's greater than a half. If you add up 8 things that are all greater than 1/16, that's greater than a half, and so on. And therefore, it's clear if you tell me I want enough terms so that the sum exceeds 10, I say that's easy to do. There's 1, 2, 3, and I'll just do a quick calculation to figure out how many groups of terms I need in order to get a total of 10. So that proves that this series diverges. So, knowing that, let's see what we can say about this budget. So what can we say? We can say that after a very long time, the probability that the budget is unbalanced after year n goes to 0, right? What I mean precisely by that is if you want to be assured that the probability that the cumulative budget will be out of balance by less than 0.001, I say just wait 1,000 years. For any year after the 1,000th year, the probability of that imbalance will be less than 1,000. We can also say that the probability that the budget will be unbalanced in any of 100 years after n years goes to 0. How do I do that?
What does that mean, what you just wrote down?
Okay, let me explain exactly what I mean by that. I say, I want to be sure that when someone takes office responsible for this budget over the next 100 years, that the probability that in any of those 100 years the budget will be out of balance can be made less than 1%. And how do I do that? I just wait long enough so that the probability that it will be out of balance in the first of those years is less than 1/100th of 1%. And since the probability is less than 1/100th of a percent for any of the individual years, the probability of the union of those events, that it's out of balance in any one of the years, is going to be less than 1%. But there are some statements that I cannot make. And this is what makes the law weak. We cannot say that the probability that the budget will ever be unbalanced again after n years goes to 0. And this might be felt to be a desirable property. The cabinet secretary says, I'm willing to wait a very, very, very long time, but I want to be sure if I wait that long time that the probability that we'll ever see an unbalanced average budget again is less than 1%. And I have to say, I can't do it. Because when I add up the probabilities for the individual imbalances, I can start with 1,000,000. I've got 1/1,000,000 plus 1/1,000,001 plus 1/1,000,002. If I keep adding terms, I can make that arbitrarily large. There's no way I can guarantee you that that's less than 0.01. And that's the sense in which this is a weak law of large numbers. And I'll get to your question in a minute, Robert. An equivalent way of stating this is that the probability that the budget is unbalanced only finitely many times goes to 0. We can't say that because with this model, the probability of an unbalanced budget does go to 0, but it goes to 0 so slowly that what we expect to happen if we wait forever is that infinitely many times the budget will be out of balance. Okay. Everyone see this? If you do, you're better than me, because it took me about half an hour to grasp this concept. So this is weak because while the probability goes to 0, it goes to 0 so slowly that if we take all the events running out to infinity and add up their probabilities, we can't put any bound on that sum. That's what it means for a series to diverge. Okay, now what I want to show you is that there is a strong law of large numbers that will let us make these statements too. If we can show that our budget model satisfies the strong law of large numbers, we'll be able to say, hey boss, wait long enough and I can prove to you that the probability that we'll ever see an unbalanced average budget again is less than 0.01 or whatever small number you choose to give me. And I can also show you that the sum of a lot of independent, identically distributed random variables with expectation 0, sort of roulette wheel things we've been talking about, satisfies the hypothesis for that strong law of large numbers. So we now come to the last topic in the course. Yeah, oh, Robert, yes.
The third line from the bottom, P unbalanced in after of. That's
sorry. That's
okay.
In any of? Is the first after supposed to be any?
In any. Thank you. It's rare to have a typo that makes something so incomprehensible I can't figure out what I meant. But any is certainly an appropriate word there.
I
Okay?
think that's the way you said it. When you
Okay. Okay, so we now come to the last topic in the course. So this is number 5, large numbers strong. This is a rather unsatisfactory proof, but it's the only elementary proof I know. The reason that it's unsatisfactory is I have to make an assumption that is not necessary for the conclusion of the theorem to be true, but is necessary for my proof to be valid. And a lot of professional mathematics is devoted to inventing new proofs that get rid of hypotheses that are made for the sole purpose of making the proof sail through. So the assumption I'm going to have to make is that the expectation of x to the fourth, sometimes called the fourth moment of the random variable, is finite. It is not difficult to concoct mass functions for which the expectation is well defined, the variance is well defined, but this quantity, when you write down the infinite series for it, turns out to be given by a divergent infinite series and doesn't exist. And for some of those random variables, the strong law of large numbers holds, but my proof won't apply to those. What this number is doesn't matter. The only thing that it matters is that it's not infinity, and this is necessary for the proof, but not for the theorem. Necessary for proof, not for the theorem. I know a proof that doesn't make this assumption, but you wouldn't want to see it. Okay, so here's the rationale behind this. When I used Chebyshov's inequality, I got an n squared in the denominator, right? And the problem was that the variance in the numerator had an n in it, and that n in the numerator killed off one of the powers of n in the denominator, so we got a 1 over n. If we had a bigger power of n in the denominator, then we might have been left with an n squared in the denominator, and I'll prove this for you too, but the sum of 1 over n squared converges. So if we can show that the probability of a large value falls off like 1 over n squared rather than just 1 over n, then we will have a strong law of large numbers. And it turns out this is really quite easy to do. We just use the basic inequality with the function being x to the 4th. However, before we can do this, we have to do some cagey reasoning about the quantity s sub n to the 4th. What we're going to do is take n of our random variables, add them together to get s sub n, and then raise it to the 4th power. And then we can use the basic inequality to make a statement about the probability that the absolute value of Sn exceeds some certain quantity. Now let's think about what happens when you write this out. What's the first term you write down in the expansion of this? x1 to the 4th, yeah. What's another term you'd write down?
X2 to the 4th.
x1 cubed times x2. But how many terms are there going to be for that?
4.
4. Very good. And then there's going to be terms like x1 squared, x2 squared. And how many times is x1 squared, x2 squared going to show up when you expand this?
6.
6. Wow, you're fast. Okay. And then we've got all sorts of other terms where we won't have x1 times x2. We'll have x7 cubed times x8 and x4 squared, x5 squared, and so on. We'll have lots and lots of terms. However, there are only 5 types. And only 2 of them matter. The first one is going to be terms like x1 to the 4th. How many terms like that are there going to be?
1.
N. There's going to be x1 to the 4th, x2 to the 4th will show up, x to the n to the 4th. We'll have n of these. And we already know that for each of them, the expectation is this quantity m. Okay. Now we've got terms like x1 cubed, x2, and I don't really care how many of those there are, because x1, x2, x3, and so on are all independent random variables. What can you tell me about the product of functions of 2 independent random variables? x1 cubed and x2 are independent random variables. The expectation of a product of random variables, if the variables are independent, is equal to the product of the expectations. But if we're assuming that each of these x's has an expectation of 0, then this is 0. So any term that has an odd exponent anywhere in it is going to average out to 0, basically because these x's are equally likely to be positive and negative. So we don't have to worry about those. There's only one other type that we have to worry about. x1 squared, x2 squared. And I think I will try to get this one right. How many pairs of two distinct subscripts can we get out of 1 through n? N choose 2. Subscript pairs times, and you've already given me the answer for this, how many ways are there to select the two factors that have the first subscript and the two that have the second subscript out of the 4? 6. 4 choose 2. So if you want to get this exactly right, this is n times n minus 1 over 2. This is 6. There are 3 times n times n minus 1 such terms. So when we multiply this out and take the expectation of s sub n to the 4 is going to be n times m. That's from these fourth power terms, plus 3 times n minus 1 times the expectation of x1 squared multiplied by the expectation of x2 squared. But all these x's have the same probability mass function, and they have an expectation of 0. So this is just the variance of x times the variance of x, right? Again, I'm using the fact that if random variables are independent, the expectation of the product is equal to the product of the expectations. So we've actually calculated the expectation of s to the 4th, and in the notes, I've done this all out. The reason I did it all out is that in Sturzaker's other book, he's got the count of the number of the terms wrong for some of the terms that average out to 0 anyway. And I started trying to recheck the calculations. It disagreed with his, and I was worried that it might disagree on the one that really matters, which is this one. In fact, we agreed on that, but I worked them all out and made sure that the total number of terms is indeed n to the 4th when you add them all up. Okay, so I think in order to keep things in sight, I'll have to go back to here. Okay, so now we'll go back to our basic inequality. And the basic inequality says the probability that the absolute value of s sub n will exceed some quantity, which I will continue to call A, is of course equal to the probability that the absolute value that s sub n to the 4th, which is intrinsically positive, equals s to the 4th. And we know that's less than or equal to the expectation of s sub n to the 4th over a to the 4th. Everyone happy with this? This is the same stupid inequality that I proved at the beginning. It's very crude, but as you see, it's crude but effective because we're going to get a very, very powerful result out of this. So yet again, I'll set A equal to n times epsilon. That is, I'm concerned about a budget imbalance that is equal to the number of years of budget multiplied by some small quantity like 1%. And now I can say the probability that S sub n divided by n exceeds A over n, that and that are certainly the same thing, is less than or equal to the expectation of S sub n to the fourth, but we work that out. That's n times m plus 3n times n minus 1 times the variance of x squared divided by n to the fourth. Now, when n gets large, which of these terms in the numerator makes any difference? The one with the n or the one with the n squared? Only the one with the n squared matters when n is very, very large. And that's why I don't give a hoot how large m may be. Once n gets large enough, this is the only term that matters. So I need to assume that m is finite. If m is infinite, the proof fails. But if m is merely very, very, very large, the proof sails right through. So what have we got? The probability that the absolute value of S sub n over n exceeds some small fraction, epsilon, is going to be less than or equal to, I'll throw this term away, and I'm just going to lump this all together and call it C. It is just a number. It doesn't depend on n. And because here I have 3n squared over n fourth, I'll cancel my n squared against the n fourth, and I still have 2 powers of n left in the denominator, which is what I was shooting for. So this is the strong law of large numbers. So what have I proved? I've proved you take any random variable with an expectation of 0, easily achieved by subtracting off an appropriate constant if it wasn't 0 to start with the property that the expectation of x to the fourth is finite. You average together n independent copies of that variable. And what I have proved to you is that the probability that that average exceeds some quantity epsilon, which you can specify as small as you like, is less than or equal to some number c. It'll depend on your choice of epsilon, but not on n, divided by n squared. So that every time you're willing to increase n by a factor of 10, you get an extra factor of 100 in the denominator of your probability estimate. In other words, we're able to show that the probabilities in this case really go to 0 much, much faster than the weak law was able to show us. Everyone comfortable with that? Now, what is this good for? Well, no, I'm going to need the whole board for this. Last thing. Now this is subtle, which is one good reason that it's not going to be on the final exam. But I think you'll get the general idea. Remember our goal. Our goal is to be able to say, hey boss, if you're willing to wait long enough, I can guarantee that the probability that the budget will ever again in the history of the universe be out of balance is less than 1% or any other epsilon that you may choose. the probability that this unbalance will ever happen again goes to 0. Quite in contrast to the weak law, which says in any given year it goes to 0, but it'll keep happening over and over and over again and eventually happen an infinite number of times. That's the difference between the n and the n squared in the denominator. So what we want is the probability that S sub n divided by n is greater than epsilon for any n greater than or equal to some capital N. And there's a fancy way of writing this down. This is a union of events, isn't it? If I choose capital N equals to 1,000, it's the union of the event budgets out of balance after 1,000 years, budgets out of balance after 1,001 years, budgets out of balance after 1,002 years, and so on. And the only nasty thing about this is it's an infinite union. But that's okay, because we have been working throughout this course with a theory of probability where our axioms say the probability of an infinite union of disjoint events is equal to the sum of the probabilities of those events. So this is the probability of the union from n equals capital N to infinity of the event S sub n divided by n is greater than epsilon. Does everyone see this? All I'm doing is taking the probability that the budget's out of balance after capital N years, capital N plus 1 years. I'm taking the union of all those events going on forever. And we know that if these events are independent, the probability of that union is the sum of the probabilities. If events are not independent, then the probability is less than or equal to the sum of the individual probabilities for the union. Special case of that, inclusion-exclusion. The probability of A union B in general is the probability of A plus the probability of B minus the probability of their intersection. And by induction, I think this was on the makeup quiz, it's easy enough to show that the probability is less than the sum of the probabilities of the individual events. So we've got the sum from little n equals capital N to infinity of the probability that the average is greater than epsilon. And this we now know is some constant over n squared. We can take the constant outside. And we've got here 1 over n squared. Now, I think most all of you learned in a calculus course, and many of you probably remembered, that this series converges. But there's such a simple proof that is different from the one you see in calculus books that I want to show it to you. Let's write out what this is. This is equal to 1 over capital N squared plus 1 over capital N plus 1 squared plus 1 over capital N plus 2 squared plus dot, dot, dot. And if I replace one of these n's in the denominator by the smaller quantity n minus 1, I make this bigger, don't I? So in each of these terms, I will do that. And now aren't you glad you got a little experience with partial fractions on the homework? Can someone mentally write 1 over n minus 1 times n in terms of partial fractions? Yeah, this is 1 over n minus 1 minus 1 over n. Okay? Someone want to do the next one? 1 over n minus 1 over n plus 1. The next one is 1 over n plus 1 minus 1 over n plus 2, and so on into the night. That cancels, that cancels, that cancels. The terms keep getting smaller and smaller, so the last one doesn't matter. So that shows that this sum is less than 1 over n minus 1. And by the way, if you did this in a calculus course, the standard way it's done in a calculus course is to write down an integral that is larger than the sum. That's an integral of dx over x squared, which is easy to do, and you show that that integral is equal to 1 over the lower limit. So this is essentially the same proof. It's just done in finite terms. Okay, so that shows that by making this capital N as large as suitably large, we can make this sum as small as we want. And isn't that great? Because in our real world situation, we now we figure out this quantity C. This quantity C depends on the variance of the random variables we're adding together, and it also depends on the epsilon that our boss hands to us. You know, the boss is very fussy and says, I want this average never again to go out of balance by more than 1%, then C is going to be larger than if it'll settle for 10%. But we can figure out this C, and then we choose capital N so large that this probability of this infinite union of events, the probability of the union of the events that the average of these random variables exceeds epsilon for any value greater than n, which is now going to be less than C times n minus 1, is less than some quantity, sort of traditional to call it delta, that someone may specify. So if the boss says, my delta is 0.05, I want to guarantee that the probability, if I'm willing to wait long enough, that the average budget will ever again in the entire future history of the universe be off by more than epsilon is less than 5%. We can say, boss, you got it. N is equal to 3,975,000 years. But we can always calculate it. And now you see, we can say two things that we couldn't say before. We can certainly say, as we said before, the probability that this average will be greater than epsilon in any individual year goes to 0 very rapidly as n gets large. And for any finite succession of years, we can make it go to 0. A little faster than before. But we can say two things we couldn't say before. We can say that the probability that it is ever again unbalanced after year capital N, goes to 0. We couldn't say that on the basis of the weak law, and in fact I showed you a model that conformed to the strict statement of the weak law for which this wasn't true, and the more conventional way of saying this is that it's unbalanced only finitely often. That is, if you average together these random variables and keep track of the averages, from time to time the average is going to drift off 0 by some small percentage. But what the strong law says is that's going to happen only finitely many times, in the sense that there will come a point where you can say the probability that it will ever happen again becomes arbitrarily small. Whereas with the weak law, we were always faced with this risk that it would happen infinitely many times. Yeah, Jerry?
So the difference between the strong law and the weak law is the power of n.
Yes, exactly. It's the power of n in the denominator. If we can get these probabilities to go 0 to 0 as fast as n squared, then when we add up the probabilities of the individual events to get something that's larger than the probability of their infinite union, we get a convergent series and some finite quantity, whereas if we have only an n in the denominator, the corresponding sum is a divergent infinite series, and we can't make such a statement.
And there was one other question. The colloquial use of the term law of averages sort of says that it's something about the real world, that the averages will come out of if you repeat the thing enough times in reality, that you'll get close to the predicted probability.
That's the correct statement of the law of averages.
But
yes.
this is a purely mathematical result. This doesn't really say anything about the real world at all.
No. Yes, it's a purely mathematical result, but this is what connects our theory with the real world. Because, you see, for the entire course, we've been pulling probabilities out of a hat. The probability is whatever the person who wrote the problem chose to say, and on a strictly axiomatic basis, we've been computing new probabilities based on old probabilities. Sometimes, very subtly, we assume the probability of a step in either direction in a random walk is a half, and we calculate the probability that the random walk last returned to 0 after 78 steps or something like that. But we've been taking our probabilities as sort of God-given. And now we see a way that we can actually estimate probabilities whenever we have a mechanism that generates independent random variables. All we have to do is average those random variables together, and we can show that the probability that that average differs by some amount from the expectation of the random variable goes to 0 if we average enough things together. And therefore, if we want an estimate of the expectation that's probably correct, that is, that has only one chance in 1,000 of being significantly off, we can always average together enough things to achieve that. And people use this all the time. You're trying to figure out, is Johnny Damon a good hitter? The first fellow who saw Johnny Damon come to the plate 7 times and got 3 hits said, this kid looks good, but you can't sign a $53 million contract on the basis of 7 at-bats. But Johnny Bateman's been playing baseball for a long time, and it's now reasonable to say, assuming that each at-bat is an independent event, that is, that he doesn't get a serious injury or something like that, we have a pretty good estimate of the probability that Johnny Damon will get a hit when he comes to bat against some randomly chosen pitcher in the American League. And that's an estimate on the basis of which George Steinbrenner was willing to stake, $53 million. But people really do rely on these laws of large numbers. This is a valid mathematical basis for estimating probabilities and estimating expectations.
As a slightly more consequential result. This is sort of what like ties statistical mechanics to thermodynamics, that the numbers are so large.
Yes. You shouldn't have asked. If I answered that question, we'd still be here at midnight because this is one of my favorite subjects. But yes, in statistical mechanics, what you're doing is dealing with cases where n is typically around 10 to the 23rd. I should say, we have a cat who has been in his life a great hunter. He's expert at dispatching small rodents. And in our backyard is something the kids put together, which is known as Boot Hill. You know, these garden stakes, and on each of these has been written 6 times 10 to the 23rd to indicate that there's one mole buried under that. But anyway, when you do statistical mechanics, typically you'll be dealing with, say, a mole of helium gas, and you'll talk about things like what's the average energy of a helium molecule, and now you're averaging over 10 to the 23rd, and the effect of this is that the actual values match so closely to the expectations you calculate that it looked in the 19th century like certainty, and that was called thermodynamics. Okay. Other questions about that? Or we got a few more minutes, or anything else? Let me conclude with a little bit about the final. You can look at your handouts for this, but I just want to make a few more comments. So, the way I put the final together is I've got a number of long problems, and with considerable effort, I have made them almost all roughly equal in length. The benefit of doing that is I can say you can now leave one out because they're all worth the same amount. There is one long problem that is shorter than the others, and this is one of these, what's the probability of throwing 10 with 4 dice or something like that. A chance for you to show that you know how to do something with generating functions. And I'll just come right out with it. You're going to see one of those on the practice exam, and you're going to meet its clone on the real final. Things that might show up in the long problems, Munchkin problems. Everyone knows what a Munchkin problem is, right? Some variant of the Monty Hall problem. Something involving binomial distributions. A coupon problem. Actually, coupon is the wrong term for this course because we didn't do it in that context. But remember the tartan dice problem on the homework. That would be much too hard for the final. The photographs of deans emailed to you. Things involving sums of geometric random variables, possibly where you have different parameters for the different geometric random variables. Almost certainly, since this didn't get a chance to make it onto a quiz, what I would characterize as a gambler's ruin problem. That's one of those problems where you set up the recurrence for p sub n and calculate the probability that you will reach the level of ruin if you were going to quit whenever you were 3 ahead, or the probability of ever being 4 ahead if you decided you'd quit if you were ever temporarily broke. So you should certainly be sure that you can set up one of those recurrences and solve it. And this is one of these things where I did a numerical example in class largely for this reason. Doing one of these numerically is actually much simpler, I think, than doing it symbolically. When done symbolically, it looks like a mess. But when you put in actual probabilities, like a probability of 2/5 of winning your bet and 3/5 of losing it, then things come out quite easy to work with. Something involving the ballot theorem, which we haven't had on a quiz. Craps has shown up enough times that I have tried to invent at least one crappy problem for the final. Generically, craps is one of these situations where you have a situation where sometimes you win, sometimes you lose, sometimes you play another round. And we've had things like that showing up since the start of the course. Something for random walks where you have to know that this infamous U sub 2n is the probability of just about anything you can think of, and particularly that you be able to explain this sort of thing in terms of one-to-one correspondence between different types of paths, to show that two things have to be the same because I can match up each path of one type with a specific path of the other type. And then a generating function problem. And finally, something we haven't done is a problem where you use conditional expectation in order to turn a potentially infinite series type of problem into a simple equation that you can solve. I did a couple of examples in lecture, which, though simple of their genre, were far too messy to put onto the final. But there are simple examples like this where the reasoning is really no more complicated than what we did tonight, breaking it up into two cases, either f of x is greater than a or it's not greater than a. There's not enough space for long problems on all of these things, and what I have tried to do is, when I ran out of long problems that would fit into 2.5 hours for the final, I wrote some little multiple choice items for the rest. So if you see something on the practice exam that looks like an important type of problem, a Munchkin problem, a Ballot-Theroux problem, a Monty Hall problem, at the very least, there will probably be some multiple choice item on the real final that covers that. And there may be things on the real final that are longer problems on the same general theme as the multiple choice items you'll see on the practice final. Things we won't have. No reversing the order of summation in a double sum. Either you can do it or you can't, but nobody really likes to do it, and it's a waste of time. And having put sums in conjunction with the Poisson distribution on both the second quiz and its makeup with not entirely satisfactory results. Usually I like to think a word to the wise is sufficient, and in this case a word to the wise was not sufficient. People tended to get it wrong the second time the same way they got it wrong the first time, which leads me to conclude that's just too hard for this course, so we're not going to have any more of those. And since we had that cute problem with verity and mendacity on the quiz, I think we're sort of done with false prophet problems. They're fun, but no space for them. And nothing on laws of large numbers, Chebyshov's inequality, or what I did tonight, simply because it's too close to the final. If you assimilated something from this lecture, that's great, but I'm not going to ask you about it 2 weeks from now. Other questions about what might be on the final? Okay, so I will email everyone the practice exam over the weekend. We'll meet this time next week. I will work each problem, and then you can ask me about it. And if time permits after that, I'll answer any other questions you have.
The final is
2 weeks. I've got authorization to let the final last 2.5 hours. I gave my word that I was writing a 2-hour final exam. But most people, when they write 2-hour final exams, there are people who don't get finished. I think if I give you 2.5 hours, that should be enough time. And we're going to have the exam in here.